Most people believe that the universe was an infinite and ageless entity, until Einstein's theory of general relativity shed some light on the principles of gravity, and Edwin Hubble's work showed us that the galaxies are moving apart from each other. There are many misconceptions that people believe about our universe's birth. The most common one being that the singularity from which our universe started grew unstable with time and eventually exploded. Well, the universe never actually did explode. The singularity started to stretch within itself and till now continues to do so. The temperature inside the singularity was unimaginably high. In such an environment, energy manifested in the form of tiniest particles known as gluons. From these gluons, pairs of quarks were created. These quarks were highly unstable and their short-lived interaction with each other formed more gluons. Because of this, instead of one ultimate force of the universe, there were now several forces that started acting within the singularity. By now, the universe had stretched to more than 1 billion kilometers in diameter, which led to large decrease in temperature. This sees the formation of new quarks, and the existing quarks started forming new particles called hadrons. The universe is now cool enough to allow the neutrons that are reasonably stable for any length of time to decay into protons and form the first atom, hydrogen. After millions of years, when hydrogen gas clumped together under the effect of gravity, an enormous amount of pressure was built, which resulted in the formation of stars. Clusters of these stars formed galaxies that we see today.
Till now, we have understood that the universe is expanding. But how can we measure this expansion? The idea was established by the brilliant Russian scientist Alexander Friedman, who proposed his assumptions and put forward his equations, which were derived with the help of general relativity. His assumptions were that the universe will look identical in whichever direction we look, and this would also be true if we were observing from anywhere else. Later, when Edwin Hubble found that the universe is expanding, Friedman's equations were found to be accurate, which helped the scientists to form the three models of our universe today.
Friedman's first equation helps us to understand these models. Here k can be either +1, 0 or -1. The first model suggests that the density term is larger than the rate of expansion term. The gravitational force between galaxies will be more than the rate of expansion of the universe, and the stretching of the universe will stop, causing the universe to collapse. This kind of universe will have a positive curvature and will look like a sphere. The second model suggests that the density term is lesser than the rate of expansion term. The gravitational force between the galaxies will have no effect on the rate of expansion, and the universe will stretch forever. This kind of universe will have a negative curvature and will look like a horse saddle. The third model suggests that the universe is stretching at such a critical rate of expansion so as to just avoid its collapse. This kind of universe will have no spatial curvature and will be flat. This equation suggests that the total mass of a universe is not dense enough to counteract its own rate of expansion, which in turn suggests that its shape should be saddle-like. But numerous experiments have shown that the universe is flat. So how does this equation cater to our flat universe? Here, the cosmological constant comes into play, which gets added up to the density term and cancels the rate of expansion term, thus making our universe flat.
One can now safely assume that the universe might have begun with just a singularity. Now this gives rise to many questions like, was our the only universe to be formed, or are there any other universes in the cosmos which were formed just like ours? Maybe we'll find out someday, or maybe not.